In the last video, we learned about all of the selection rules that go into determining the spectra of the hydrogen atom. In fact, we learned the selection rules also for many electron atoms, but we're still focused squarely on the hydrogen atom right now. And now to close out the discussion of spectra, we're going to talk about the Zeeman effect. Or in other words, we'll talk about how to understand the fine structure in a magnetic field. If you think back to how we motivated this originally, we started by looking at the splitting of the electronic energies as you turned on the magnetic field. And the original statement was that if you're looking at all of the possible transitions that go from the n equals 2 levels to the n equals 1 level, once you turn on a magnetic field, you should split your original singlet, so one single transition, into 3. But then this really simple idea crashed against reality, and we saw from real spectra that in fact these 3 lines we expected turn out to not be 3 but 10. And this was a part of the motivation for why we started to look at spin-orbit coupling in the first place. But once we have a handle on spin-orbit coupling, we now know everything we need to know in order to go back and figure out what happens to the energy in a magnetic field, and in particular what happens to the splittings in a magnetic field. Okay, so if you have a hydrogen atom sitting in space and you turn on a magnetic field in the z direction, it will interact with both the angular momentum, so the Lz, and the spin angular momentum. And you will get a perturbation term that looks like this. Okay, so out front here we have the Bohr magneton radius divided by h bar. And then we have the angular momentum, the orbital angular momentum in the z direction, plus this anomalous spin factor times the spin angular momentum also in the z direction. And all of this is proportional to the magnetic field that you have here. Okay, so this is what the perturbation term looks like. And it turns out this leads to a shift in the observed energies. We're going to write this as delta E mag. So this is just the change in each of the energy levels that is a result of turning on a magnetic field. And this will be equal to G of JL beta B, again the Bohr magneton, times m sub j times bz, where bz is the strength of the magnetic field in the z direction. Okay, so let's go through this. So this G is what's known as the Landé G factor. So it's basically just taking into account the fact that the orbital angular momentum has a different factor in front of it than the spin, right? So the spin has this extra factor of 2 up here, and because the eigenstates are normally complex combinations of L and S, because there's the total angular momentum that's conserved, that means that these are more complicated structures. That means that they combine in complicated ways, and so instead of having a simple number for this G, you have this G depends both on J and L. There's a formula for the Landé G factor given in the notes and in the book, but I'm not going to repeat it here because the fine structure of it is actually not that important for our needs. Okay, so next we have the Bohr magneton again. And then finally we have these m sub j's, which again are the quantum numbers that correspond to the total angular momentum. Right, so that means that m sub j goes from minus j plus 1, and so on, up until you get to positive j. So let's just make a little room real quick. And so now the most important part of this is that this g is a number that is normally between 1 and 2, but it is fixed for a particular value of j and l. And so now it means that you have different splittings depending on the different m sub j values that are in here. And so now this means that all of the different m sub j values that corresponds to the same atomic term symbol will split when you put them in a magnetic field. And they split according to j, not L or S, but to j. Okay, so now let's look at all of the possible lines that we can see from the n equals 2 level to the n equals 1 level. So the same selection rules apply, which means that we can only see transitions that correspond to doublet P to doublet S. And so that we're just going to look at the levels that correspond to these. And now we're going to see what happens when we turn on a magnetic field. So this dashed line here is showing the energy level for this state without a magnetic field. And now for this doublet S, it has J equals 1/2. And so that means that when you turn on a magnetic field, there will be now two values of m sub j. You have +1/2 and -1/2, which means that these two will split up and down. So this turns into a doublet that goes up and down in a magnetic field. And so this one line splits into two. When you look at the doublet P up here, it starts off at this dashed line. And again, because this is a J equals 1/2 state, this means that you have two different values of m sub j now. You have +1/2 and -1/2. And then when you turn on a field, these will move in opposite directions. Now for the doublet P3/2 state, so this has allowed values of m sub j -3/2, -1/2, 1/2, and +3/2. So that means there are four different allowed values of m sub j for the j equals 3/2. And so that means that this one state, when you turn on a magnetic field, will split into four different states. Okay, and now in this particular case, we have one more selection rule that comes into play because all of a sudden we have another way to split the energies. And this is a selection rule on m sub j. So we see that delta m sub j can equal 0 or ±1. So this is in addition to the delta L equals ±1, delta S equals 0, and delta J equals ±1 or 0 if J is not equal to 0. Okay, so now we can go through and look at all of these possibilities. So if we start with the doublet P1/2, so up top we have the MJ equals 1/2. And so now based on the selection rules, we know that this state should be able to go to any of the doublet S1/2 states where m sub j is equal to 1/2, 3/2, or -1/2. And so because here the only possibilities are 1/2 and -1/2, it means that this upper state, if you look at this line, this connects mj equals 1/2 to mj equals 1/2, and then up here you have mj equals 1/2 to mj equals -1/2. Okay, if you do the same thing for the second line, you see that this can also go to two different places, and so that gives you four lines in total that come from the doublet P1/2 to the doublet S1/2, and these get drawn here, so this one line splits in four. And now we take a look at the doublet P3/2, and here we have to pay more attention to the selection rules. So if we start off with the very top one, this is an mj equals 3/2. Okay, so that means that this state can go to an m sub j ending value that is either 3/2, 5/2, or 1/2. And since there are no values of 5/2 or 3/2 in the doublet J1/2 multiplet, this means that the only way that this can get down to the S state is to go down to mj equals +1/2. Okay, and that's what this line is here. And notice that this is the only line that's coming off of this mj equals 3/2. And now the flip will also be true if you look at the mj equals -3/2. This will only be able to make it when mj is equal to +1, which means that we go from mj equals -3/2 to mj equals -1/2 here. And that will be the only line that connects this mj equals -3/2 to the doublet S1/2. And now for the doublet p 3/2 with mj equals plus and minus 1/2, they actually follow the exact same pattern that we saw for the doublet p 1/2. Where now each of these two lines can go down to either of the two lines for the doublet s1/2, which means that there are 4 transitions that correspond from mj going from plus or minus 1/2 down to mj equals plus or minus 1/2. Okay, so if we add all these up, we have 4 lines going from the doublet p1/2 to the doublet s1/2. And then we have 6 total lines going from the doublet p3/2 to the doublet s1/2. 2 of the lines correspond to transitions out of mj equals 3/2 or mj equals minus 3/2. And the other 4 lines come out of mj equals plus or minus 1/2. Okay, now with that, you know everything you need to know to understand the fine structure of atomic spectra in a magnetic field.